What's up, YouTube? Welcome to this introduction to WebSockets. This video is in preparation for SignalR, which is going to be coming in a later video. In this video, it's WebSockets, which is one of the underlying technologies in use in SignalR. But I felt that I can't necessarily talk about SignalR without basically explaining WebSockets, and then I can't explain WebSockets unless I talk about HTTP and TCP and TCP IP and so on and so forth. So this video is going to be a deep dive to some extent on TCP, UDP, and then protocols, specifically HTTP and WebSockets. I hope that will then help you or prepare you or put you in a better place to understand just WebSockets and then SignalR eventually when we do that. SignalR is a toolkit on top of all of this stuff. So you don't necessarily need to know how SignalR is implemented and how things work. But as is usual with me, I need to understand how shit works. And so I'm hoping that people like me who also need to understand some of the stuff under the hood. And so here it is. So I'll put chapter markers underneath and if you on the timeline, hopefully you'll see that. So in case you want to skip through to certain parts, go right ahead. Personally, I'd sit and watch the whole thing. Of course, I wouldn't have made this in this way, but I understand some people are in a rush to just get to the bottom of things. I'm going to start with a demo. This is a real world kind of demo. So I'm going to show you some things. So here is a device. This is a hardware device. And think of this as a UI where it's a bar chart with 3 bars on it. Now what I'm going to do is I'm going to start a application on my desktop that's going to indirectly be sending messages to this device. So let's take a look at that. And you see the bars are sort of moving up and down. Now this happens to be, let's call it the UI of an application. Of course, it's all working with WebSockets and a bunch of other protocols. I'll show you like a slide of how everything works. But here's this application. And I'm going to also use my phone. So, and you should see, hopefully, that these two devices are in sync in terms of their data. I'm hoping you can see that. I'll also show you a screen where maybe all of these will be in sync. So I'll keep this here. I'll also open up the screen here. A lot of stuff going on simultaneously. So now I'm basically showing you the screen here, and I'm going to add editing. I'm going to try and show you kind of both of these, the hardware and the screen. Okay, so that's the demo. And I'm going to explain to you how this works, and then we're going to dive deeper into TCP, HTTP, and so on and so forth. All right. Okay, so I'm going to turn this thing off. All right, so everything's been shut down. Actually, it's not. Let me shut this down. All these devices and lights flashing in my eyes. Okay, so if you look at the screen here, you'll see that I'm going to show you, try and explain to you what you just saw. So you get a sort of the lay of the land, if you will. The device that I showed you, let's say, is this device, the one. Okay, it doesn't look anything like it, but it's one of the CPUs or the MCUs, if you will, microcontrollers that I'm using on that device. I just use that image here to indicate that's the device. The application I ran on my desktop machine was this one. This is a regular .NET Core application talking HTTP, posting through a Web API or a ASP.NET Core Web API or ASP.NET. It's actually an very old application, so it's ASP.NET application. It's really talking just standard HTTPS and making requests into like a post or a put request into an endpoint on a ASP.NET application. So this is nothing unusual here. Once this ASP.NET application receives the data and it does what it needs to do with it, it then using WebSockets. So this is a .NET Core .NET application that's talking WebSockets, and it publishes data to multiple clients, any clients that have connected to it. So my phone was connected to it. This device indirectly is connected to it. The web browser on my machine is connected to it. So it's essentially taking the data received, did what it had to do with it, and then it sort of publishes or broadcasts that data. It's not a broadcast in terms of UDP, so I don't want to confuse the issue in case anyone knows what UDP is. It's a TCP broadcast, but it's a broadcast in the sense it's sending it out to multiple clients. Okay. And so in this case, I'm showing you my phone, and this is WSS, which is WebSocket Secure. It's just like HTTP and HTTPS. There's a WS and a WSS to indicate WebSocket and WebSocket Secure. And so these are the multiple clients. So I only showed you one desktop client, if you will, that was also interested in that information. But then I have another client, which is a Raspberry Pi application that is a receiver, if you will, of the messages that are being broadcast by this application on the server. And this application in turn takes that data and then sort of translates that WebSocket protocol to another protocol called MQTT-S. MQTT-S or MQTT is a very, very old technique. It's a pub-sub technology. It was introduced, I think, in the 80s. Okay, so this was used by hardware people way back, before IoT existed. Hardware devices did talk to each other, like on the factory floor and things for factory automation. They were confined to their kind of local network. There was no internet at the time, so they certainly established their own networks within the factory, and then devices could talk to each other as pub-sub. So this protocol has been around since then. Today it's a standardized protocol and it's open source, so anyone can use it. In the IoT field, we use MQTT instead of AMQP or AMQPS. It's a much lighter protocol, very perfectly suited to smaller devices with hardly any resources in terms of memory and CPU, processing power. You could use this from C#.NET as well. So there's libraries for MQTT, and I actually do that in many applications. But in this case, this is in fact, it's a .NET application, a .NET Core application in this case, that is running on the Raspberry Pi, that is converting my data that came in as WebSockets, and then rebroadcasting that same data using the MQTT-S libraries. And it's sending that to an MQTT-S server that's out on the internet. And this happens to be the Service Bus logo, so I got a bit confused. I'm just trying to show this is a message broker, since MQTT-S is also a pub-sub. And then the device that you saw, this application, the device is subscriber to an MQTT-S channel or topic. And therefore, any messages published by this application using WebSockets is received by like the phones and desktops and things of that nature simultaneously. That message is also being received by this Raspberry Pi application, which then converts that into MQTT-S, publishes it, and now I could have a whole host of IoT devices that respond to the same data. So it's a mixture of WebSockets primarily, but then also MQTT or MQTT-S as one of the protocols I'm using. But I think today libraries on the IoT layer have the support for WebSockets. And I'm going to go into WebSockets some more, and then you'll probably understand things a little bit better, right? Okay, I hope you enjoyed the demo. I'm going to keep hopefully I remember all this. I'm going to keep the publisher alive. So it's publishing to the broker. You can use your browser or phone browser, and I'm going to put the URL to the endpoint. You can browse to it and you'll see stuff happening. So if you open up multiple browser instances on your desktop or between your phone and your desktop, you'll see the same information appearing on all devices simultaneously, right? So I'll keep it running for maybe a couple of days after this video is posted. So today's Sunday, I'll post it Sunday evening, Sunday night, my Sunday night. And let's say I'll keep that publisher open or publishing basically till say Tuesday night. Okay. I don't know hopefully I remember to do that. But if you're interested, you can browse. I'll put the link to the page. It's a regular page, browser page. You can browse to it through multiple browser instances or invite your friends and compare notes as to what you're seeing and how much time if there's a delay. All right. Okay. Moving on to WebSockets. But of course, I can't talk about WebSockets unless I talk about TCP. And I can't talk about TCP unless I give you some basic information. So as I said, there's going to be chapter markers underneath. If you feel this is too deep, you can skip over the next part. I personally think this is important. So anyway, I'm going to tell you what it is. So TCP has a TCP stack. And the TCP stack, typically called the OSI stack or the OSI model, and there's a bunch of other variations to that. Essentially, you want me to move? Which way? Want me to leave? Or you want me to move like that? All right. Okay, you plan to put something here? Okay. Distractions. the OSI stack, okay, it's up here somewhere. The OSI stack, the bottommost layer is the physical layer. This is, think of it like the hardware, the network card and the cabling and all that sort of thing. And then on top of that is the data link layer. The data link layer is a layer on top. It's just a stack, conceptually. The data link layer would be things like Ethernet, Wi-Fi, ISDN, various other data link protocols, at that layer. So you still write code at that layer, but it's, different kind of code, system code rather than application code. All right, and then the next layer is the network layer. So this is typically like the IP layer, Internet Protocol layer. And then after that is the network, so the transport layer, which is TCP, UDP, a bunch of other things like that. And then on top of that is typically, so I think I've got to layer 4, and then layers 5, 6, and 7 are typically normally combined as one, or sometimes the 2 are combined and whatever. So there's basically 7 layers, but you can think of it as 4 and then plus 3, and the 3 can be represented as 1. It's the application layer. This is things like application code, but if you're building a web application, you're not building the web server application, your web server. The web server itself is a layer, so which is why they break this up into 3 layers. So basically you'll have a web server, and then on top of that, you will have your application. So there are responsibilities at these different layers. So they're called applications of TCP, not in terms of, how we call application. It's the usage of TCP. When they say TCP application, it's the use of TCP. So web applications or web servers typically manage sessions. And then you have your application sitting right on top, layer 7. Okay, so that's really kind of the stack. Now, what is TCP? I want to give you a basic understanding about TCP. Then we're going to talk about HTTP to some extent, and then go to WebSockets. All right. So TCP is that bare bones infrastructure required, the TCP stack, that includes hardware, of course, interconnected machines, to have communications going on between machines in a network or across the internet as we know it now. TCP is the basic foundation for all communications across everything we do today. There used to be different competing protocols before, but right at this point is TCP and TCP IP specifically, which is the Internet Protocol. That's kind of part of the TCP protocol, or it's a stack on. TCP is a stack on of the IP protocol. In order for TCP to work, you need a client, which is an client application, and a server. And the way TCP works is the client has to initiate a connection with the server. The server cannot initiate a connection with the client. The client has to initiate the connection with the server. So the server is typically listening on a port, let's say some port, random port. And the client wants to communicate with that server. So the client has to initiate that conversation on that same port, and of course go to the same IP address where the server is listening and ask to connect. And then there's a bit of a handshake, and I'll explain later on what a handshake is. They have this kind of agreement or discussion. Machines are having, by the way, not humans. And then they move on to a different port. This is a key thing to understand. So let's say, for example, I'm switching over to HTTP just so most people understand what I'm saying. So your browser is talking to your web server typically on port 80. Let's assume it's HTTP and not HTTPS. It doesn't really matter either way. It's port 80. So there's a application, which we call our web server, listening on port 80 on some IP address somewhere on the internet, on your local machine, doesn't matter where. That server is listening, waiting for connections to happen. So let's say 2 of us try and connect to that same server at the same time. What would happen? We're both trying to connect to that server on port 80. Because one was saying that that's not going to work, and it won't. It won't. Only one of us is going to get through. So the way TCP IP works, generally speaking, basically overall, not generally, but all TCP IP protocols work like this. TCP IP, a connection is established on a known port or on a well-known port. So port 80 being the well-known port for web applications. So you establish the connection. As soon as the connection is made, so as soon as my client application, let's say we both try and talk to the same server at the same time. As soon as my client application gets through, a connection is made, they have the handshake, they have a conversation, and then the client and the server, because of the server, decide to switch to a totally different port. This is a random port, so we have 65535 possible ports. What is that? 2 to the power 1460, I don't know what it is, whatever it is, 65535 ports. So one random port is picked, and the server and the client switch over to conversing on that port. When your request reaches, it may be queued up, behind mine. But as soon as my connection and that server connection switch to a different port, your connection gets through, the same handshaking goes on, the same negotiation goes on, and the services move to this other port. Totally different random port again. So effectively what's happened is the server is listening on a given port, but as soon as a connection request occurs and it's happy or willing to connect, they will handshake and negotiate and move to a different port. So the same server is sort of randomly choosing different ports for the multiple different clients that are attempting to connect to it, which is how, we can all be watching YouTube videos, millions of us, at the same time, because it's all listening on one port. But as connections are made, they are given random port numbers. And so the conversation occurs on it. It's like saying, okay, you walk into my company, in my office, or, my company, and, you meet me, I meet you at the reception, and I say, okay, let's go to this meeting room, right? So you walked in the door here, we're not having a conversation in the reception. We go to a little meeting room and have a discussion there. It's kind of like that. So everyone that comes in goes to a different meeting room, but that's an agreement, the handshaking, or one of the things that occur during the handshaking that happens. This is pretty much standard across all TCP protocols, barring a few. UDP, for example, is slightly different. Of course, TCP and UDP are different. TCP is a connection-oriented, guaranteed delivery protocol, meaning it requires a connection to be established, and the data that is transmitted across from client to server or server to client, and as a response, is guaranteed to be delivered. Of course, that to give that guarantee, there's lots of checks and balances in place in the protocol. What we call error checking. And that's a lot of overhead to that. Error checking, retransmissions, and a whole bunch of other things have to occur to give you that guarantee. But it's guaranteed at that network layer. Right? At your application, you don't have to worry about that. That's being handled at the physical layer. So, but it's a guaranteed protocol, and it's guaranteed delivery protocol and connection oriented. UDP and use cases for TCP are things like HTTP, SMTP, POP or POP3, NNTP, NTP, and so on and so forth. Some of them you probably heard. UDP is a connectionless protocol. It doesn't have the guaranteed delivery thing. So there is the notion of a client and a server, but the server could be sort of broadcasting things, and the clients may or may not be listening. And if they catch it, that's great. If they don't, that's fine. And the other thing with TCP is the order in which data is sent is the same order in which it is received. So there's a guarantee not of the delivery, but also of the order or the sequence in which bytes appear across the wire. With UDP, there's no guarantee of delivery and there's no guarantee of order. And you must think like, what? What's the point of that? Like, why would anyone use that protocol? But of course, there are advantages to UDP in terms of less traffic, less overhead. This whole error checking and retry, all the stuff that has to happen, that's not there. So certain things do lend themselves to that. So we have DNS, DHCP, a lot of your VoIP, your voice over IP. If you use WhatsApp and other video applications, these are all using UDP, because if you lose data along the way, what's going to happen? I mean, it's not like it's the end of the world, right? I missed a certain word you said because I lost a data packet. So it's not the end of the world. So those kind of protocols it doesn't really matter. But if you're working with data in a business level, you can't afford to lose data. So for certain applications, UDP sort of makes sense. So anyway, that's the difference. That's TCP versus UDP. And then, besides the OSI stack, we've talked about TCP and the connection and the handshake. Okay, this handshake is going to become important. So now let's talk about HTTP. HTTP is an application of TCP. By that I mean it's the use of TCP. So HTTP, while TCP is considered to be the communications protocol, HTTP is considered, or HTTP, SMTP, POP, POP3 is considered the wire protocol. So sometimes TCP is considered the transport protocol and then the wire protocol. Okay. So I might use transport and communications protocol interchangeably, but that's what it means. The transport is happening at one protocol while the conversation is occurring at a different protocol using or riding on top of this. Like there's a highway, which is your transport protocol, and then there's a car, but there could be cars, there could be trucks, there could be motorcycles. Each of these types of vehicles is a different application or a different protocol, such as HTTP, SMTP, POP3, and so on the same highway, same transport. All right. Well, that was pretty cool. I've never actually used that metaphor before. All right, so HTTP is a request response protocol, meaning, of course, the client has to make the initiate the connection, and the client has to make the request, and then the client has to wait or will wait till the server responds. The server by itself will never talk to the client. Now, in earlier versions of HTTP, the connections were severed, meaning make a connection, make a request, get a response, disconnect. Make a connection, make a request, get a response, disconnect. That was HTTP 1.0. Of course, as you can imagine, that's terrible for any kind of performance. And so they changed that or improved that a few years later to include HTTP 1.1, which allowed you to maintain the connection or keep alive the header, HTTP header called keep alive. That essentially told the server, if you know HTTP 1.1, please keep that connection alive. And then the connection was established once, but then you still made the request, waited for the response, got back a response. And whenever you need it again, you could make another request and then get a response, wait for the response and come back. So HTTP is a request response protocol. HTTP is a heavy protocol in that the protocol itself has a lot of extra information as part of the protocol. By protocol, I mean the stuff that is required in order to communicate. Right, so the data is the part that you want to send across and receive, but there's a bunch of other information that needs to be handled as part of the protocol. So it's a fairly noisy protocol, especially if the data you're trying to send is small amounts of data. It turns out that the protocol is more expensive than the data, right? So what we call signal to noise. Signal means the thing that you actually want, which is the data you want to send or receive, and the noise is everything else that is required in order to send this data across. With the HTTP, the signal to noise ratio could be fairly high, especially when the data is small, right? Because things like JSON and XML the signal to noise ratio is terrible anyways. So, it's not like the HTTP part is going to kill you. The JSON is already way too noisy, and so is XML even more noisy than the data that's actually there. And we sort of got used to that. But again, this is working at the protocol layer. So, when you design things, you're not designing things for bad use cases. You're designing things as best as possible. The bad use cases are, we're just ending up doing things over a period of time. You want to make things easy for some reason, and we end up using things like XML and JSON for data across two systems, which I think is a very bad idea. All right, so once we have that established, once we understand this whole idea, the request and the response, it turns out that what if the server wanted to talk to the client without the client asking for something? Like there's times when, so what we do today, or not today, but in the past, what we would do is we'd have some sort of a timer on the browser side, in JavaScript. And as the timer expired, we'd make calls every 5 seconds, go back to the server and ask, is there more data? Is there more data? Is there something new? Is there something new? And if there's something new, you'd get back the new data and you refresh the screen. But this polling kept going on, right? So for things of that nature, or web applications where the server needs to sort of send data back without the client asking for it to update the UI, for example. If it's a multiplayer application, if your opponent moved their thing on their screen, how do you know it, right? And so the server has to initiate that call. So for those kinds of applications, WebSockets was introduced. Now, WebSockets is way more than most people think it is, right? Most people think WebSockets is just this multiplayer game and a long polling solution. It's not. It's way more than that. So that's the reason I want to make this video as a separate video for WebSockets. All right. So WebSockets is essentially sockets. So when you build your application in a Windows application, like a C#.NET, C++ application, you have the notion of a socket. The socket is like that bare bones minimum thing, class, library that allows you to communicate using TCP or UDP. The HTTP client socket is the HTTP application or the socket that talks HTTP. So it's still relying on the underlying socket, right? And it then handles the HTTP protocol, but using the TCP socket to do the work, but sort of working or talking the protocol. So that's what HTTP client is doing. The socket is this underlying thing. WebSocket is the socket that you have access to in your browser. It's a socket. For all intents and purposes, it's that low-level socket. This is called a WebSocket only because it's from a browser. So it's basically pure TCP. It has nothing to do with HTTP at all, right? It's a WebSocket, so it's a socket. It's devoid of any protocol. It's not an HTTP socket. It's a socket. Hopefully that makes sense. So basically what they've said is the browser and a server can now communicate using TCP. It doesn't have to be HTTP, right? But there's some things to consider. Today, our firewalls, proxies, reverse proxies, the devices and the software, authentication, authorization is all geared around HTTP, right? That's a lot of effort, work, infrastructure that's in place. So what they did is they said, okay, what we're going to do is this. If you and I want to talk on a different protocol, not HTTP, because HTTP is a request and a response, meaning I have to, as a client, make a request, then only then can you give me a response back, and I'll wait around for the response to come back. What if I want to talk to you in pure old TCP, some protocol of our own choosing? That's nothing to do with HTTP. And how do we do that? The way WebSockets was designed, and it's a pretty clever way of doing it, it has enabled many other protocols to work on off of WebSockets. So we call AMQP over WebSockets, MQTT over WebSockets, and so on and so forth. So there's different protocols that are over WebSocket, as WebSocket is used as what they call the tunneling protocol. And then, I'm going too deep right now, but just let me stick to this part here. So imagine a browser is in conversation with a server, regular browser, HTTP, right? And for some reason now you want to switch over to using WebSockets. The browser sends a GET. Okay, you'll see it over here. The GET protocol. It has to be a GET, HTTP GET. It has to be HTTP 1.1, the request. If you don't know what that is, just skip through. The request has to be a GET request, has to be HTTP 1.1 or higher. Sorry, not HTTP 1. Because there's HTTP 2 now. HTTP 2 is the current standard. It's not ubiquitous like HTTP 1.1 is, but that's the current standard. A lot of browsers support that. And HTTP 2 is got a whole host of other features that are just mind-blowing. Yes, stick to WebSockets. Okay. All right. So the web client browser would make a request to the server saying, hey, I want to change to WebSockets. I want to upgrade to a different protocol, different thing. I want to upgrade to WebSockets. And it sends this other header, the sec header, the key. I forget the whole header name. It's sec key, so that's the key. And a bunch of other things. All other HTTP headers are fine. And the reason I'm saying that is because the initial request is being made on HTTP, so which means we can use all the infrastructure, authentication, authorizations, proxies, firewalls, all of that will still be in action. The server will receive that first request from the client on HTTP. The only additional headers would be like the sec key and a bunch of other things, and the upgrade and the connection stuff. That's it. Everything else is standard HTTP, so you can put whatever headers you want. Once the server has understood the request by the client and allowed it, meaning that person is okay, authorized, is coming from the right same origin, and a whole host of other things that you normally do in a web application. Says, oh, but you want to upgrade to WebSocket protocol. It takes that key. It uses a magic string, concatenates the key in the magic string. Yeah, it's a magic string. It's like dark energy, the constant. Right? It's the same string. Everyone uses the same magic string. It's like a GUID. I'm not sure exactly the history behind that, but there's a magic string that concatenate these two things. They get the SHA-1 of that. SHA-1, I made a video on, forget the name title, but I'll put a link over here, explain hashing and all this stuff. So they get a SHA-1 of that. And then that server sends that back. Now, that handshake this is the part that I'm talking about, is all the handshake. Once the server is accepting that request for upgrade, the client and server are having this conversation, and the server then says, okay, let's free up this port 80, as I discussed before, and let's switch over to this other port and this other protocol. And so the server responds with a 101, HTTP 101 saying, switching protocols. And then that conversation occurs on that different port, on one of the random 65535 ports. So at that point, the browser is no longer talking HTTP. The server is no longer talking HTTP. They're both talking this WebSockets protocol, which is a very, very raw protocol. And you typically use a protocol sitting on top of that to actually have a conversation. You can invent your own, or, like what I talked about, we have AMQP over WebSockets, which means you can have a RabbitMQ or a Service Bus browser client application using JavaScript libraries that talk AMQP or AMQPS over WebSockets, or MQTT, like the other pub sub that I showed you for the device, that protocol, and a JavaScript library that allows a browser to talk MQTT or MQTTS and so on. So it has enabled the browser to be a really good or a solid or allows the browser to be a very capable client, a TCP client, right? So it's not limited to just talk HTTP anymore. So WebSockets is allowing browsers to be able to communicate using many other protocols. WebSockets is just the underpinning protocol. So you can write other protocols on top of that, like AMQP on over. That's what they call it, AMQP over WebSockets, MQTT over WebSockets, and so on. So that's the basic reason or purpose of WebSockets. Some people think it's just this, chat and long polling and all. No. WebSockets is a full-blown sort of foundational capability that has been handed off to browsers. Long polling and chatting, all that's just like one of the use cases for it. There are many, many use cases to WebSockets. All right. So WebSockets have another feature that is unlike HTTP, which is also important to understand. So WebSockets are two-way. All TCP connections, all TCP communications are, may not be. UDP is not necessarily two-way. I don't think. Well, it may be, but because of the fact that it's not guaranteed, I'm not quite sure. TCP is always a two-way conversation. Right? Clients and servers talk to each other. WebSocket, HTTP is two-way, but it's like the client has to initiate the request. The client has to make the connection, then the client has to make the request and waits for the response. The server makes a response, the client gets a response back. Server cannot talk to the client on all of its own. Right? You can't suddenly just start a conversation. With WebSockets, they have a full duplex communication. So not only is it a two-way conversation between client and server, full duplex is, if you know, like, the walkie-talkies, you have cops or security people at malls or at your company, if you're in a large enterprise, they have this conversation going on. They press that button and, like whatever noises happen. The idea being that you can hear anyone that's talking, but if you wanted to talk, you have to press this button, effectively interrupting everybody else so you can talk, and then you release the button. Now you can hear a response back. So the walkie-talkies are half duplex. They're not full duplex. Our phones, cell phones and other phones, are full duplex, meaning you and I can have this conversation. You could be talking while I'm talking. I may not be able to understand what you're saying, but I'm still hearing you. So we can both hear each other and be talking at the same time. Right? That's a full duplex. So think of a channel in, okay, look at this picture. Think of the channel being the connection that was initially established by the browser. Sorry, not channel. The connection has been established by the browser with the server initially. They do that handshake bit to WebSockets, and they kind of upgrade over to WebSockets. They're still connected, but they're talking like a different protocol, right? At that point, within the same connection, there are sort of two pipes or two channels. And these are full duplex, meaning the client and the server can both be talking to each other simultaneously. They don't have to wait for anything. The server can decide anytime to send something to the client. The client can decide to send anything, anytime, something to the server. And they both happily understand each other. No data loss, no kind of garbled messages coming like we normally hear on the phone. It's full duplex, right? And it just works. So that's the beauty of WebSockets, on top of the fact that it's using browsers or enabling browsers to talk any other TCP protocol, because it's really just a socket. It's slightly different than a raw socket. There's what we call a WebSocket frame. And once you understand the frame, within the frame, data packets go in and out, and you can then shape that data packet in a specific way. And that allows the receiving side to talk the original protocol, the AMQP, MQTT, whatever the protocol that is. Basically, the frame just exists between the browser and the server. And then beyond that, it's the original protocol, right? The other thing about WebSockets is it is super lightweight. Remember that whole signal to noise ratio I was talking about? It's like 2 bytes more than the data you want to send. Of course, now if you're sending 1 byte, then you're saying the signal to noise ratio is pretty bad. If it's like 2:1, yes, it's 2 bytes minimum. But as your data grows, it's going way beyond 2 bytes at that point. The protocol is not utilizing a lot of the bandwidth. So it's a super fast protocol as well. So they did a good job designing the fact that this giving future-proofing the browser to support any TCP protocol in the future by way of building libraries that allow the WebSocket conversation to contain additional like AMQP and MQTT and other kinds of conversations or protocols on top of that, but giving the servers and WebSockets to have this conversation, which is full duplex on top of that, and very lightweight, very fast, very lightweight, right? So that's some of the benefits. Now there are some downsides too. Well, one downside, the way it works, and I'll see if I can, yeah, okay, I don't know, but I'm going to talk as if that image is not there in case the image is not there. Typically, your browsers talk to a reverse proxy for security reasons, and then the reverse proxy talks to your web servers. The reason is that the reverse proxy hides the destination servers from the internet, right? So you don't know exactly where it's going. Generally speaking, with WebSockets, the way you would normally design a system, most people don't, but normally design the system would be, or you could design, I'm not even saying you have to, you could, just so I'm explaining this correctly. The request comes into your reverse proxy asking for HTTP, right? Regular website, routes it to one machine. And once this machine and the client decide to, is my hand being? Yeah. Once the machine and the client decide to switch, upgrade protocols, this proxy is still a reverse proxy, is still doing HTTP, right? Remember that request comes on HTTP. So it does the whole HTTP thing. And then when it switches to a different IP address, a different channel, port, it could potentially switch to a whole other machine. And that machine is purely handling WebSocket traffic. It's not handling HTTP traffic, right? So you can distribute your load that way. Nonetheless, horizontal scaling becomes a bit difficult because these connections are perpetual, right? Once the client and the server has established a connection, then this client and that server, or the number of clients attached to that server, are always going to be the same. And what if this server gets too many clients connected to it? How do you scale it? Right? It becomes a bit of a difficult problem. So that's one of the downsides of WebSockets. Cloud service providers like Azure have a WebSocket service as a PaaS service offering. So you can use that, and they handle all of that for you, so you don't have to worry about that whole thing. So, but as individuals, you might, if you're a small company, yet you got, thousands of people using your applications simultaneously, like a gaming company or something, you might have to, of course, figure out how to handle the scaling part. It's not impossible. It's just more difficult. So, and depending on the kind of proxy servers you use, layer 5 proxies or layer 7, it will be easier or difficult. Anyways, way too much detail, right? All right. I've gone so much all over the place. I apologize if this has been like chaos. As I said, I'm hoping the chapter markers on the bottom of or on the timeline will help you understand where to stop and start. I hope this has been useful. I hope you've enjoyed yourselves. If you have, please give me a thumbs up, and I will see you next time.